In this presentation, we will discuss one-way frequencies. We first encountered one-way frequencies in a previous module while discussing numerical summaries for describing data. We noted that for categorical data, it's common to present frequencies or counts and/or proportions. In that module, we examined several one-way frequency tables using the BP data and looked at gender frequencies and categorical BMI frequencies, both shown here. These tables provide information on the frequency or count of observations in each category of the variable, as well as the relative frequency or percent of the total number of observations that this count represents. In this module, we will be examining common tests used for testing hypotheses about categorical data. In this first presentation, we will be discussing one-way frequency tables. In the next presentation, we will introduce and discuss several common tests used to analyze two-way frequency tables. Let's begin with an example looking at the racial distribution of subjects enrolled in a randomized controlled trial. The racial category of subjects is given in the rows of the table: white, black, other. In the first column of the table is the frequency or raw count of subjects in the trial in each racial category. There were 69 subjects categorized as white, 25 subjects categorized as black, and 6 subjects categorized as other. The third column in the table provides the row proportions or percentages of subjects in each category. The last two columns in the table provide the cumulative frequency and cumulative percent or proportion. The research question of interest is whether or not there is any bias in enrollment by racial category. Are the observed enrollment counts in each category similar to expected enrollment? This table provides the observed and expected counts for each racial category. For this particular trial, the expected enrollment was anticipated to be 60 white subjects, 35 black subjects, and 6 other. As you can see, there were slightly more white subjects observed than expected, and slightly fewer black subjects observed than expected. The chi-square goodness of fit test compares the observed and expected numbers of subjects in each category of a one-way frequency table. The test is based on the combined discrepancies between the observed and expected counts and generates a p-value that answers the following question. If the null hypothesis were true, what is the chance of randomly selecting subjects with this large a discrepancy, or one larger, between the observed and expected distribution? To conduct a hypothesis test on this data, we would do the following. Before the data is collected, state the null and alternative hypotheses. Select a significance level and choose an appropriate statistical test that will address the hypothesis of interest, here the chi-square goodness of fit test. After the data is collected, perform the chi-square goodness of fit test and calculate the p-value. If the p-value is less than or equal to alpha, then conclude that the result is statistically significant and decide to reject the null hypothesis. Otherwise, conclude that the result is not statistically significant and decide to not reject or fail to reject the null hypothesis. For the example at hand, the null hypothesis is that there is no enrollment bias. We can state this more specifically as the observed data are sampled from a population with the expected frequencies 60, 35, 5. The alternative hypothesis is that there is enrollment bias. More specifically, we can state this as the observed data are sampled from a population with different expected frequencies. Let's specify a significance level of 0.05 for this hypothesis test. With regard to making inferences, if the p-value is less than or equal to 0.05, then reject HO and conclude that the result is statistically significant. The data are not consistent with the null hypothesis and suggest that some factor beyond random chance must account for the discrepancy in racial enrollment. If the p-value is greater than 0.05, then fail to reject the null hypothesis and conclude the result is not statistically significant. The data do not deviate from the expected distribution beyond what would be expected by random chance. This doesn't prove the null, it only says that there is no evidence against it. Without going into too much detail, let's talk about how this test works. For each category, white, black, other, calculate the difference between the observed and expected values. Square that difference. Divide that square by the expected value. Add up the result of step 1 for all categories. The result is a chi-square value equal to 4.41. The chi-square value also has an additional characteristic associated with it known as the df, or degrees of freedom, which is equal to the number of categories minus 1. Here the degrees of freedom equals 3 minus 1, or 2. If the null hypothesis is true, the chi-square distribution with degrees of freedom equal to 2 is known, and you can use statistical software to find the p-value that corresponds to the calculated value of the chi-square equal to 4.41 with 2 degrees of freedom. Here is the formula for calculating the appropriate chi-square value. This is what we generally refer to as a test statistic, a formula or equation used to generate an appropriate test value from which a p-value is calculated. Calculation of the test statistic and the p-value will be demonstrated later using StatCrunch. The resulting p-value for the racial distribution example is 0.11. Since our p-value is greater than 0.05, we fail to reject the null hypothesis and conclude that the result is not statistically significant. In other words, there is insufficient evidence to indicate that the observed counts in each category deviate from what is expected by random chance under the null hypothesis. One could argue that based on the result of this test and the magnitude of the deviations observed in the table, a reasonable conclusion is that this data provides no evidence of enrollment bias. That's all there is to the chi-square goodness of fit test. Some closing comments. The chi-square goodness of fit test is based on approximations that are generally accurate as long as the expected value under the null hypothesis in each category is greater than or equal to 5. The expected values selected for the null hypothesis are intended to reflect what you would expect to see on average in that category over repeated experiments under the assumed distribution. Note that there are no accompanying confidence intervals for this test. In general, the chi-square goodness of fit test is summarized using a p-value and clinical interpretation of the discrepancy between the observed and expected frequencies. This concludes our discussion of one-way frequency tables.